Okay, here goes. So since I have all of Redox in one big bundle, I'm going to zoom through the stuff we're done with from before, but I figured I'll just keep it all in one big bundle. So here's what you're supposed to know. Here, focus forward on the stuff for voltaic and electrolytic cells. Obviously, we learned all about redox reactions. What is oxidation? What is reduction? How do we assign oxidation numbers? This is a hodgepodge of practice. This is going to be the worst video ever. There's, again, some practice on balancing those equations. So, and we're just going to move through all of this really quickly because I know it's going to show it to you anyways. We did look at the reactivity series in the earlier half, and I want to hit that up again now because this really comes up with our voltaic cells. Remembering that those more reactive metals are going to be the strongest reducing agents. So when we have a voltaic cell, the more reactive metal is going to be the one that gets oxidized, right? Because it is the one that is better at shoving off its electrons. Okay, so remember that. And then, you know, the same thing with the nonmetals. The more reactive are further down. That doesn't come up as much in our cells. Blah-de-blah, moving forward. There we go, we're back, sorry. So we looked at voltaic cells, so I want to make sure we cover all of this. Voltaic cells are also called galvanic cells, and basically we're harnessing the energy from a spontaneous redox reaction, right? These reactions, when they're spontaneous, they would naturally lose some heat. So by setting it up in a voltaic cell, we are essentially separating the two half reactions that are really only connected by that transfer of electrons. There's no exchange of chemicals, the needed, it's just the electron transfer. So by keeping those half reactions separate and having the electron transfer happen through a wire, we're able to capture the energy. Sorry, okay, 9. Here is our generic diagram of a voltaic cell. Two different ways to see it, right? We have the full picture where we're showing the anode and the cathode and the salt bridge and the electrons moving and the whole deal. And then you have this more condensed form, this, what did we call it? I forget. The cell diagram convention. There we go, I remembered. So cell diagram convention is shown at the bottom of the screen where you see phases separated by a single line and cells separated by that double line. That double line could represent the salt bridge. This is always written to show the direction of electron flow. So the zinc metal loses electrons to become the zinc ion. Then those electrons are grabbed by the copper ion to form the copper metal. So there's your voltaic cell summary. Over here, we did a little zoom in class to kind of try to help us recognize why the heck is everything doing what it's doing. So in addition to the potential being set up to where that zinc electrode gets a little negative and that copper electrode in relation is then a little positive, we also can see that we get this charge buildup in our salt solutions. And without the salt bridge connecting those both, we don't have a finish of we don't have our circuit being finished, but also that charge buildup would kill the those equilibrium reactions, right? You would not be able to proceed in the directions we want to. So that kind of shows why the salt bridge needs to exist, why we need ions to travel the way we need to. Then just today, we started talking about electrolytic cells, and we talked about electrolytic cells as basically being the opposite of a voltaic cell. Basically. Here we're using a non-spontaneous redox reaction, but we're forcing it to happen by adding electricity. And the purpose of this is to free elements from ionic compounds. So we are producing elements during this process and using a lot of energy to do so. We looked at the parts of an electrolytic cell, a power source, electrolyte, electrodes, and electrical conductors or wires. And notice here we talked about the kind of convention for diagramming out that power source or that battery. You might recognize this from physics. The long side is the positive side of the battery, and the short little line is the negative side of the battery. Then here we go, we created our electrolytic cell. Notice one big difference is everything is in the same container. We could set up an electrolytic cell in one beaker. And in this case, the electrolyte is the thing that is undergoing chemical change. Those electrodes are inert, they're doing nothing. It's either going to be an inert metal or it's going to be graphite. They're really just there to allow the reactions to happen kind of next to them, essentially, releasing electrons onto them or taking electrons off of them. So we see in our example here, sodium chloride is our electrolyte. So in solution or in a molten state, you're going to have sodium ions and chloride ions. And since the electrons are originating from from the negative end of that power source, that is our negative side of our electrolytic cell. So the electrons come from the negative side of the power source, right? We have I put this on a different slide, but I'll go ahead and do it here for you really quick. Hopefully this doesn't make this thing crazy, right? We are starting right here. This is the starting point for an electrolytic cell. So that's where the electrons are coming from. That determines that to be the negative side of our cell. So the electrons come down onto the cathode where the reduction of the metal happens. So the sodium ion, right, that is the one that wants the electrons. So it's going to be reduced to form sodium metal. And again, this is happening because the battery or the power source is shoving electrons onto it, forcing this non-spontaneous reaction to happen. Once that happens, we now have this kind of pull for those electrons coming into the positive end of the battery, causing that other electrode, the anode, to be relatively positive, which is going to cause it to attract those chloride ions. Once they get over there, that draw for electrons is really powerful from the positive side of the power source. So the chlorine atoms, or the chlorine ions, give up their electrons to form chlorine gas, releasing electrons to complete the circuit and go back into the positive side of the power source. So in summary, in an electrolytic cell, you have oxidation happening at the anode, like always, but this time that's the positive side, because in an electrolytic cell, the cathode, where the reduction is happening, right, the electrons are coming from that battery. So that is in fact the negative side. So we see that at the cathode, cations add electrons from the energy source or the power source, and anions are releasing electrons back to that power source. And here we go again. So I think I just kind of repeated these notes. I apologize. Right, but here, same picture again. I don't know why I'm showing this to you a million times. I feel like these are weird extra notes, but that's okay. So on the voltaic cell, right, when we're comparing voltaic and electrolytic cells, again, I do not recommend just memorizing this. I really recommend doing a quick sketch of the cells, kind of like I've shown below here, to make sure that you're straight on what is happening where. So the anode is always the site of oxidation, but for the voltaic cell, it is negative because it is that oxidation reaction that is releasing the electrons. So that's where the electrons start from, so that's the negative side. For the electrolytic cell, though, the oxidation is actually the positive side. The cathode, again, is always where reduction happens. For the voltaic cell, by default, it is the positive side because the oxidation side is the negative. But on the electrolytic cell, the reduction side is the negative side because that is where those electrons are coming from. They're coming from the battery being shoved into that redox or that reduction reaction. And again, voltaic cells are producing energy, using the energy, or producing electricity, using the energy released from that spontaneous reaction, i.e. batteries. And electrolytic cells are using electricity to force a non-spontaneous redox reaction and produce elements. And blank screens. There's the quiz we took, there's the quiz we took, and there's these notes again. So there we go. It's going to go through and show you all of this again anyways, so I might as well yap you. Final summary. And then in class, we looked at these last couple questions, and we saw that for, let's do an example for 16A for KBr, right? K is going to be our positive ion. Bromine is going to be our negative ion. So potassium is going to add electrons to become potassium metal, whereas bromine will release electrons to become our bromine gas. We need to balance that, sorry, 2, 2, and there we go. So we see that potassium is adding an electron, a gain of electron is reduction, so this is our reduction half, therefore this is our oxidation half. Then we could talk about where this is happening and all of that, but we don't need to for this question. Then we went down and we looked at number 18. You can do 17 on your own, bring it into class, that would be great. But if you look at number 18, I did recommend, and for this one you don't actually need it, but in general, I really do recommend to just cruise through the cell in question before even looking at the options, because those multiple choice questions, remember, they will screw you up. So we're looking at electrolysis of molten copper 2 chloride. So I know that that's going to form copper 2 plus and Cl minus, right? So I know that the copper 2 plus is going to need to add electrons to form the copper metal, and I know that the chlorine is going to produce chlorine gas and release electrons, right? Therefore, there's my battery, There's my electrons coming in, out. There's my electrons coming in. This is the source of my electrons. So this is the negative side. This is the positive side. Then we see that this is where the reduction reaction is happening. So that's my reduction. This is my oxidation. Reduction is always the cathode. Oxidation is always the anode. I know this is getting messy. Normally I would do this much smaller for myself, but you know, I'm doing it for you, so here we go. So now I'm going to look at the possible answers. Copper ions and chloride ions move through the electrolyte. Absolutely, ions are always moving through the electrolyte. That makes sense. Oxidation of the chloride ion takes place at the anode. Oxidation always happens at the anode, but what about chloride? Is that happening? Yes, the chloride ion is being oxidized, so that's legit. Electrons move through the external circuit. Absolutely. And then lastly, oxidation of chlorine takes place at the cathode. Well, no, it doesn't. First of all, oxidation never happens at the cathode, and here copper is doing its stuff at the cathode. So D would be the one that does not fit. That's the way I would work through multiple choice questions, especially on these ones, just to make sure that I'm on the right track. All right, let me know what you think. This one was a little chaotic. We'll do better getting into new material with shorter slides, I think. Okay, enjoy.